Hello friends, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. In last video, I discussed about the reactivity of substitution reactions and their factors. So one factor I have already discussed about the nature of alkyl groups. So in this video, I will discuss about nature of solvents. You know, nature of solvent also play very important role in SN1 and SN2 reactions. The nature of solvent plays a dominant role in deciding the mechanism and rate of substitution reaction. You know, usually ions are stabilized by solvation in good ionizing solvents, and therefore substitution reactions producing ions from neutral reactants, which is accelerated by a good ionizing solvents. You keep in mind the SN1 reactions begins with the initial ionizations of neutral molecules, and thus it is facilitated by good ionizing solvent. Cations are solvated by solvent molecules through coordination with electron pairs, whereas anions are solvated by solvent molecules through hydrogen bonding. You can see here this Rx react with water and forming R plus and X minus. Hydrolysis occurs. On the same way, if this R is solvations of cation, means this is your water molecules and this is your water molecules, this carbocation is stabilized by solvations. And another, this X minus, if water is there, it is stabilized by solvation of an ion through the hydrogen bonding. So because of these bonds, the energies of transition state of an SN1 reaction is lowered. You know, my friends, in SN2 reactions, the most common case is the reaction of an anion, reactions of an anion with neutral molecules. A good ionizing solvent slows down the reactions because it stabilizes the reactant more effectively than the transition state. So, the ionization properties of different solvent is reflected in their dielectric constant. For example, water with high dielectric constant of 81 would be much more effective ionizing solvent than methanol, with the dielectric constant of only 33. The ionizing power of some common solvent is found to be in order: water greater than formic acid, greater than methanol, greater than ethanol, greater than acetic acid. So, it is sometimes possible to change the mechanistic course of substitution reaction by changing the polarity of solvent. Methyl bromide, which normally undergoes hydrolysis by SN2 mechanisms in aqueous alkaline methanol, hydrolyzed by the SN1 mechanism in formic acid containing a small amount of water. So you can see here CH3Br undergo SN2 reactions forming CH3OH. If you change the solvent, in place of ethanol, you can take the formic acid and OH minus, here is water. So this path is favored by SN1 reactions and this path is favored by SN2 reactions. Why? Due to solvent effects. Now, third important point is nature of the living groups. You know, my friends, living groups is also play a very important role in substitution reaction. The reactivity of substrate in substitution reaction is partly determined by the nature of the living group. Since the living group breaks away as a base, weak bases are easier to displace than the strong base, and thus we may generalize that the less basic the substituents, the more easily is it displaced by the solvent in SN2 reaction, SN1 reaction, or by an attacking nucleophilic reagent in SN2 reaction. For example, alcohol are resistant to the substitution reaction in non-acidic media because of the strong basicity of the OH minus group. which makes it a poor leaving group. However, in presence of acid, the hydroxyl group is displaced as water, which being a weak base is a good leaving group. Consequently, alcohol undergoes substitution reaction only in acidic medium. So look at here, this ROH in equilibrium, it forms ROH2. Y is positive charge because here 3 bond to the oxygen. Now you can see the formation of alkyl radicals after removing water, and further this nucleophile attack on this center through the SN1 forming RBR, and this nucleophile attacking here and forming RBI and water. So this path is SN1 and this path is SN2. Why? It depends on the leaving group. So other strong bases which are very poor leaving group in substitution reaction are H minus, RO minus and R2N minus. In case of alkyl halide, the easy of separation of halide is the order I greater than Br minus greater than Cl minus greater than F minus. This is the reverse of the order of carbon halogen bond strength as expected. In general, we can say the weaker the basicity of a group, the better is its leaving ability. Weak bases are always stable bases as they are not bonded as strongly to the carbon as strong bases. A weaker bond is thus easier to break, as larger atoms are better able to stabilize their negative charge. The relative basicities of the halide ions are weakest base I minus, Br minus, Cl minus, and F minus is the strongest base. So, as weak bases are better leaving group, relative leaving ability of halide ions follow the order best leaving group I minus. Just remember, best leaving group I minus in comparison to F minus, worst leaving group. Relations of the alkyl halide in SN2 reaction thus follow the order most reactive Ri, Rbr, Rcl, Rf, least reactive Rf. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching. In next video, I will discuss about nature of nucleophilic reagents. This is the fourth factor which is affecting the reactivity of substitution reactions.